Over a 30-day period, the moon appears to completely alter its physical shape in the night sky. A common assumption is that these dark curves are caused by Earth getting in the way and casting its shadow on the lunar surface. But the reality is different. When Earth blocks the sun's light directly, it casts a distinct shadow that creates a lunar eclipse, a specific, relatively rare event. This top-down model shows the geometry. The sun keeps exactly half the moon illuminated. The changing shapes result from our shifting viewing angle. Orbiting forward, more sunlit area becomes visible, the waxing period, peaking at full moon. Continuing, the bright portion shrinks during the waning period. The moon isn't physically changing. It is acting as a massive, highly predictable geometric clock hanging in our sky. Beyond the shifting light, the moon exerts a massive, invisible physical force on Earth through gravity. This cross-section shows the moon's gravity stretching Earth's oceans into distinct tidal bulges. The bulges stay locked toward the moon while Earth rotates inside. As a coastal city spins into deep water, it hits high tide. In the shallow edge, low tide. But the moon is also moving forward in its orbit every day. Earth must spin an extra 50 minutes to catch up to the moon's new position, which pushes the high tide 50 minutes later each day. The cosmic dance between the Earth and the moon physically drives the daily shifting rhythm of the entire ocean. Earth's own motions give us our other basic units of time. A single rotation defines the solar day, and a full orbit around the sun creates the solar year. Historically, humans measured that daily rotation by tracking the sun's highest point, watching as the shadows cast on the ground grew shorter, then longer again. This scale illustrates a persistent mathematical mismatch. A solar year takes roughly 365¼ days. A lunar month takes exactly 29.5 days. 12 lunar months fall short of a full Earth orbit by about 11 days. Different calendar systems fix this gap in different ways. The Gregorian calendar accounts for the extra quarter day in the solar year by adding a leap year every 4 years. Traditional lunisolar calendars take a different approach. Every 2 to 3 years, they insert an entire extra intercalary month, called Adhika Masa, to pull the lunar cycle back into alignment with the seasons. These mathematical corrections directly dictate when millions of people celebrate major cultural festivals. The precise arrival of the new moon determines the exact date for Diwali, the Festival of Lights. Conversely, the exact opposite lunar phase, the full moon, sets the date for the vibrant color-throwing celebrations of Holi. Some traditions, like Makar Sankranti, follow the solar calendar instead, tying the kite-flying festivities to the sun's specific transition into a new constellation. Human calendars are ingenious mathematical bridges, engineered to keep our local seasons and traditions locked into the orbits of the solar system. Modern space technology has moved us past simple observation. We now launch our own artificial satellites into orbit to monitor the planet from above. India plays an active role in this frontier through ISRO, the Indian Space Research Organization. They engineer and launch rockets that deliver payloads to study everything from the lunar surface to the atmosphere of Mars. Missions like the Cartosat series constantly scan the ground to provide high-resolution mapping, predict severe weather patterns, and manage disaster response. This map of low Earth orbit highlights a severe consequence of that rapid expansion. Those glowing red dots represent the dense, chaotic accumulation of space debris circling our planet. Defunct satellites, lost tools, and spent rocket stages travel at thousands of miles an hour. At those speeds, a piece of junk the size of a coin can violently tear through a multi-million-dollar active mission. Securing the future of orbit requires international agreements and active engineering, like designing thrusters that force old equipment to safely burn up in the atmosphere before it crashes into anything else. Comprehending the massive scale of these orbital mechanics usually starts on the ground, inside public institutions like the Nehru Planetarium. Planetariums provide the telescopes and immersive sky shows necessary to turn abstract physics into observable reality. By looking up and understanding the mechanics of the sky, we learn to measure time, navigate our oceans, synchronize our culture, and ultimately build the technology to explore the universe ourselves.